The benefits from the use of satellite. There is a direct investment of at least $185 billion in launch, construction, and ground networks. There's an investment multiplier for satellites, consumer benefits, and there are socio-economic benefits, which are very difficult to quantify. And the socio-economic benefits include safety and emergency communications, scientific research, digital inclusion, broad choice of service options, connectivity. We know that Malawi was recently badly affected by cyclones. In the case of cyclones or adverse weather conditions, we find that often terrestrial infrastructure has been destroyed, and this again is where satellite can come into its own in providing communications when terrestrial infrastructure has been deployed. Again, this is a repeat of much of what I've said, and this is from the report again, and the report is available on the GSOA website at gsowasatellite.com, where we look at use of spectrum in the 7 to 24 gigahertz bands. Within geostationary orbits, as I said, there are 600 satellites already in operation. Half of these approximately use Ku and Ka bands. These satellites are valued at around $200 million each. In non-geostationary orbit, we have over 6,000 satellites, which are valued at around $2 million each. So you can see the numbers there of investment and direct and indirect investment. And we will talk a little bit later on about the number of satellites and the proliferation of satellites in orbit and possible problems that could come about as a result of this. So having had a look at the history and where we are we going with SATCOMs? And we break this up into two segments, the space segment and the ground segment. I said earlier that previously satellites were expensive and they had limited bandwidth. If we look at the space segment, we now have high throughput satellites or even very high throughput satellites, which are software defined. We no longer just have the bent pipe scenario. And satellite communication is really undergoing an incredible phase of growth and innovation. This makes resilience and reach of SATCOM the biggest asset and brings significant benefits to society. And they help to bridge the economic and digital divide across the globe, particularly important in rural Africa. The result of these new SATCOM services, different orbital altitudes, whether it be GEO, MEO, or LEO, and the trend is then to provide more affordable, efficient, and reliable connectivity in the most difficult to reach places. So these advances, I beg your pardon, reduce infrastructure cost. We have more efficient payloads. There's new propulsion systems, including electric propulsion. Satellites have lower mass. They have different designs. We have increased payload flexibility. There's a resilient end-to-end groundwork, lower cost launch vehicles. We all know about reusable rockets even. And there is also a lower cost in terminal user equipment. Your high throughput satellites are capable of providing from 50 to 200 gigabits per second, and will even go up to 1 terabit per second. So there's innovation in all the satellite bands, C, Ku, LS, Ka, QV. So we have software-defined satellites, no longer the pure bent pipe. There are also multi-orbit networks. Traditionally and currently, you have a satellite in GEO which provides a particular service, or you have a satellite in LEO. Going forward, we will have multi-orbit networks, and we'll get to this a little bit later, where you would have seamless integration of GSO and non-GSO satellites in a single solution. There will be end-to-end coverage. There are already companies that are providing direct-to-user 5G services via satellite, and this is going to be a huge advantage going forward in areas that are hard to reach. So we are looking at ubiquity, continuity, scalability, reliability, and reach. And as I mentioned in the introduction, satellite will contribute to achieving the Sustainable Development Goals. Currently, 74 million people benefit from telemedicine via SATCOM. There are over 80 million students that can benefit from SATCOM teleeducation, and there are projects by GSOA members in Africa already on the ground. Again, you will find more details in the VVA-LS Telecom report. I'm certainly quite willing to make this available to the organizers as well, who can share these reports with participants at this conference. So, looking at satellite orbits, and as I said, up to now, you have had a satellite in GEO providing a service. You've had a satellite in non-GSO providing a service. But if we look at these different characteristics, looking at GEO, the latency, as we've seen earlier, is not great, of the order of around 500 milliseconds. Not a problem for fixed satellite services, but when you get to mobility, it can be a problem. The bandwidth is good. Economics of geosatellites is favorable. You have good security, you have good reliability, and there's availability. Medium Earth orbit, you have better latency than you have with the GEO. Your bandwidth, again, is good. The economics is not bad. Security is not as good as it is with the geostationary, as is the case with reliability, and availability is also not as good. Remember that a single satellite will not provide you with continuous coverage. You need a fleet of satellites. Low Earth orbit, you have fantastic latency. Your bandwidth is okay, economics okay, security, reliability, and availability are not that great for a number of reasons. And therefore, the way forward for SATCOMs is to have a multi-orbit capability where you combine the best factors of the GSO, and non-GSO, including both low Earth orbit and medium Earth orbit. This will give us the best of both worlds to achieve what we need. Satellites are capable of providing wide area coverage, both urban and rural, and this is really where satellite comes into its own in the African context, in a completely rural or mostly rural environment. Satellite, the initial capital cost is high, but as you expand your network, that capital cost does not increase, as is the case with terrestrial networks. With terrestrial networks in an urban environment, you have a good return on investment, but as you get into a completely rural area, you find where you have lower population density, lower usage of the satellite, your costs become prohibitively expensive. And this is what we're trying to show here, that particularly in the African context, for a completely rural environment, satellite is, we believe, the best way to go. So here is the GSOA net view of what this multi-orbit network would look like. You would have a satellite in GEO with multiple satellites providing a single beam perhaps to maritime and another beam to oil rigs off the coast. You would then also have multiple frequency beams from GEO into aircraft. People that are involved with the ITU World Radio Conference will know about the Earth stations in motion. You've got direct to home. You've got transport terrestrial vehicles, and then you've got the base stations. These satellites, complemented by medium Earth orbit and low Earth orbit, provide this coverage. And the future of satellite connectivity is definitely going to be a software-defined, multi-layer, multi-orbit network of networks, which will then also be capable of feeding into terrestrial networks, be they fiber or be they terrestrial wireless networks. And we'll talk about that a little bit more going forward. So up to now, you've had a standalone satellite network, you've had a terrestrial network that's been standalone, and you've got certain aeronautical networks. Going forward, there will be a partial integration in the 5G environment where you will have an integrated design. But once we get into 6G, you will have a fully integrated network where your satellite and terrestrial infrastructure will be totally integrated. And we will see this in the 3GPP, I beg your pardon, release 17 standard, where there are already not what they call non-terrestrial or satellite networks integrated into the 5G broadband terrestrial network. I think we have already covered this, where satellite supports 5G differentiators, different orbits, and you go to the cloud. You can provide to data centers, you can provide aircraft, terrestrial, direct to home, ships and planes. You've got coverage, availability, latency is not an issue in a multi-orbit network. You've got the density of coverage, you've got security, and you've got the economics. So again, this integrated multi-orbit configuration is definitely the way we're going to see things moving in future. I spoke earlier about direct to end user or direct to device. And currently, the broadband market has been dominated by mobile operators, being the only operators that can provide to, for example, your mobile phone. With 3GPP release 17, we are now seeing this renaissance of non-terrestrial networks or satellite companies providing a new service. And there are a number of these that are currently in existence, and the number is growing. And we give some names of some of those that are providing this service. So you will already have the opportunity, and going forward, it will become more available, that non-terrestrial networks will provide a new and independent service in difficult to reach areas direct to the end user or direct to device. These are just some examples of broadband via satellite, where you connect again to aircraft, ships, terrestrial mobile services, to the internet, to terrestrial base stations. So I've spoken about the 3GPP standards for satellite. Release 17, which was completed in December 2019, provides the standards for satellite broadband, mobile broadband, and this really marks a landmark in the breakthrough for non-terrestrial network standardization, where before mobile broadband was purely terrestrial. Now we have the option of both
recording in progress
of terrestrial and non-terrestrial networks. And currently we are looking at frequency ranges below 7 gigahertz, just because of the bandwidth restraints that there are. So we are looking at the S and the L bands in release 17. Release 18 will look at further frequency bands, higher frequency bands, and also look at additional features, providing additional use cases and enhanced performance for mobile broadband via satellite. 5G is only now being implemented, but already there is look at 6G. And the 6G enhancements are being looked at in 3GPP release 18. They're looking at resilience. They're looking at increased capacity requirements. They're looking at accelerating the deployment of networks. And 6G will definitely rely on combined benefits of multiple communication technologies for broader society, and SATCOMs will play the key role. For 3G, 4G, where terrestrial has been the key technology, we believe that by the time it comes to 6G, satellite will really come into its own. Release 17 is pretty much a hybrid. There will still be a mix, but by the time we get into 6G, satellite will come into its own in providing end-use mobile broadband. So, as I've said, consumer devices are being built with integrated mobile service connectivity. There's voice, there's email, there's texting. These services will expand with the new standards that are done by 3GPP, and new devices will ensure connectivity available to anyone, anywhere in the world. Again, particularly important in the African rural context. Yeah, we are looking at, again, some of the, I beg your pardon, I'm going too quickly, at some of the benefits of satellite, where in mining, in agriculture and fisheries, and in many more applications, satellites will enable connectivity needed to foster sustainable and safe communities. And these, again, will be seamless in the case of natural disasters. Satellite is the technology that can withstand these natural disasters. So the multi-orbit end-to-end system is based on these standards. You've got geo satellites, you've got LEO satellites, and you've got the terrestrial networks. And these will essentially complement one another going forward. You will connect to the internet, to public clouds, to consumer networks from your local networking and cloud applications. An important issue, and I will touch on this very briefly, and I am in fact nearing the end of my presentation, is space sustainability. I think we all know of mega constellations in non-geostationary orbit that are being launched. The geostationary orbit has approximately 600 satellites. This is going to increase. In non-geostationary orbit, there are currently 6,000 satellites. This is certainly going to increase with these mega constellations, and there are a number of different companies that are launching these mega constellations. So space sustainability is becoming more and more important. And this is also particularly important for developing countries where our gateway into space is via low Earth orbit. You will recall that I mentioned earlier that a geostationary satellite might be of the order of $200 to $300 million. A low Earth orbit satellite is probably a tenth of that cost. So this is low Earth orbit, non-geostationary orbit is the gateway for developing countries. The satellite industry shares a common interest in space sustainability and ensuring that space is available to all in the long term. However, there are diverse views on how best to achieve this. As I've said, there are huge private investments, mega constellations, and a satellite in orbit can last up to 20 years. Even once it has reached end of life, that satellite remains in orbit for a long period of time. So we need to look at how we can manage this process to ensure that space is available for all. Disruption in space affects all users. It harms customers. It impacts adversely on services. And this can be for a number of reasons, whether it is collisions, whether it's interference. There can be other causes. There have also been cases where there has been intentional destruction of satellites, and this creates major problems for the satellite industry and for users, more importantly. So within space governance, I'm falling over my words here. You have the Interagency Space Debris Coordination Committee, or the IADC, which exchanges information on identifying space debris mitigation. You have the United Nations Committee on the Peaceful Uses of Outer Space. They govern 5 international treaties. They also have principles and guidelines for long-term sustainability of outer space activities, and in fact have 21 long-term sustainability guidelines. The ITU has best practices on space. There is a recommendation on environmental sustainability of geostationary orbits. The European Union has space sustainability guidelines. The Space Development Agency, or the SDA, also has guidelines. And coming forward in the future, the EU is looking at improving its space sustainability guidelines. Space traffic management standards are being put in place. And next year, there is a proposal for an EU space law to address what rules need to be developed regarding space sustainability. Here are some questions for you to ponder upon, and we are not going to get the answers here today, but think about them going forward and outside of this particular conference. How many satellites and systems can safely share the low Earth orbit? Is it 10,000? Is it 20,000? Is it 100,000? We need to look at this. And how best can this sharing of low Earth orbit be achieved? Bearing in mind that this is the orbit where developing countries will start their space journey. What steps should be taken to maximize the opportunity to utilize low Earth orbit? What is an approximate post-mission deorbit time frame? How do we deorbit satellites? You may be aware that just recently the FCC has fined a particular satellite operator for incorrectly deorbiting a satellite that was not in agreement with what had been decided it should be done. And while this fine was not a significant amount, I think it creates a very important principle. Maneuverability of satellites is fundamental, but how does one do this, particularly with small sats, which are low costs? And what are the reliability metrics that satellites should be designed to achieve? And how do we improve this in this fast changing environment? Something for you to ponder on going forward, particularly for the space agency. When you start licensing satellites, you may wish to look at some of these issues in your license conditions. So new systems continue to emerge, and there's a steep learning curve for all of us. We are still trying to understand what the appropriate issues are, how to regulate emerging systems, and without stifling innovation. It is very important that we continue to look at new innovations. How best do we do this? There are some harmonized rules. There are other countries which have unique rules. What can we learn from this? What do we do? Where do we get our best practices? But importantly, dialogue between policymakers and the satellite industry is and will remain critical. And this is where GSOA stands ready to support you, to provide advice wherever we can in your journey going forward in the satellite field. As I've said, it is one of our missions to support governments, to assist them to achieve their space goals, and we are at all times available to provide support, assistance to you in this particular regard. So there are diverse views on how to address space sustainability. And these views do not mean there's a reduced commitment to space operations. However, collaboration is very much a must in this particular issue. It is not one person that needs to solve this problem. We all need to look at this together. And again, GSOA, amongst its 70 members who comprise GEO operators, LEO operators, and operators that operate in both the geo and the non-GSO space do this. Chair, with that, I thank you, and I hand back to you. If there are any questions, I will do my best to attempt to answer them. Thank you. Thank you very much for those questions. I think as far as the effect of weather on satellite goes, you will recall that even in low Earth orbit, you are situated approximately 1,000 or more kilometers above the Earth. And as you go into medium Earth orbit and into geostationary orbit, you go even higher. So weather is not going to affect your satellite at all because you are above the atmospheric conditions. The one advantage of satellite, as I indicated, that where you do have things such as cyclones, where your terrestrial transmission infrastructure is destroyed, your satellite infrastructure can continue to provide services there. Regarding the lifespan of satellites, typically, yes, a geostationary satellite might have a lifespan of around 20 years. Now, you must remember that this is electronic equipment on the satellite. And while a terrestrial tower may have a longer lifespan, the electronic equipment on that satellite will certainly not last for 30 or 35 years. There will also be technological improvements that will require you to upgrade your terrestrial infrastructure. And similarly with satellites, you will want to upgrade the capability of your satellite to take account of the improvements in technology. Coming to the question on the IADC guidelines and other guidelines, there are a number of guidelines available. And as I say, this is something that is very much under discussion at the moment. You've got the EU, you've got IADC, you've got the UN Committee on the Peaceful Uses of Outer Space. So there are a number of issues here. There isn't a fix-it at the moment, or a single fix-it. People are looking at options, and different people have different ideas. I happen to be involved in the development of the United Nations Committee on the Peaceful Use of Outer Space guidelines, and there were a number of different views there. So what one needs to look at is how best can these guidelines be adapted to suit your particular issues, remembering that these are guidelines, they are not mandatory requirements for support. On the question of limited bandwidth, again, this was traditionally the case, but now one also needs to discuss what is limited bandwidth. Currently on satellite, we are capable of getting 100, 200 megabits per second to a user. For e-learning as well, what you can do is the bandwidth is limited. You don't need to access it all the time. You can have a store and pause where you can download learning material overnight and distribute it to learners the next day. However, again, with new satellites, that bandwidth is increasing, and e-learning is certainly possible. The use of direct-to-device satellites going forward, again, will facilitate e-learning. Thank you very much. Yeah, a very interesting question. Now, currently, light communication is not being commercially deployed. It is certainly something that can be looked at in the future. From a satellite perspective, possibly not in the near to midterm. As you are all aware that if you shine a torch in a room, the beam, once it hits a wall, it stops. So for light communication, would really be very short range. Certainly you have a very high bandwidth. You can provide a lot of data over that, but in the short term, it would not be feasible for satellite communication. Also, in terms of the International Telecommunication Union, the radio frequency spectrum is defined at stopping below the frequencies which are applicable to light communication. So they are currently not regulated within the international community, but for short-term and for very short range, light communication is an option for the future. Thank you. Technically, yes, it's possible, but as I say, if you look at the current infrastructure, the current scenario, your radio frequency spectrum, and I mean this includes satellite, television, broadband, etc., goes up to 3,000 gigahertz or 3 terahertz, which is way below the frequencies used by light communications. Lasers are an option for terrestrial coverage, but at this stage, not for satellite communication. Thank you, moderator.
It's only, excuse me, I can only see from my end just the first slide. My name is David Hua Blantyre. I'm saying I can only see the first slide. And I've seen comments from others to the same effect as well.
Recording stopped.